Here's the solution to question 4 on the Physics 211 practice exam. This is very much like question 1, so you may want to watch those two videos together. Here we're imagining Chara the dog, starting here, accelerating up to her top speed. We don't know how much distance she covers during that. We'll figure that out. Then she runs at a constant speed for a long time until she gets to a rabbit hole, 30 meters away. She overshoots the rabbit hole. The rabbit's gone back down to its hole. And she runs past the hole as she tries to accelerate to a stop, and then accelerates backwards. So in this part, she is accelerating forward. In this part, she's running at a constant speed. And then during this entire motion, she's accelerating backwards. Here she is running forward at a decreasing rate. Here she's running backwards at an increasing rate. It turns out that we can do this entire thing using these graphs. We may not need to write any equations at all. So the first thing we want to know is how much time the rabbit has to duck back into its hole before Chara gets there, and then how far Chara overshoots. So what the problem asks you for is for the time here and for the position here. But we really need to figure out everything, right? We're supposed to graph these things. We got to figure out everything about this motion. It turns out this is pretty simple. So I'm going to do this, color coding this using the same colors that I've drawn the stages of the motion here in. So we know her acceleration while she is speeding up is 4 meters per second squared, but her top speed is 12 meters per second. 12 divided by 4 is 3, so it takes her 3 seconds to get to her top speed. Notice that each of these tick marks is 2 seconds, so it'll take her 3 seconds to get up to speed. Now, the crux of doing this is remembering that the area under the velocity versus time graph is the distance traveled. So this is a triangle, right? Let's label this here. So this mark is 3 seconds. And I have a triangle with a height of 12 meters per second and a width of 3. So 1/2 base times height here is 18 meters. So this means that she covers 18 meters while she is accelerating. Ooh, we figured something out. This is x equals 18 meters. Might as well put that on our position graph, shall we? So let's see. So in 3 seconds, she winds up at 18 meters, which is here. This is a function which is increasing with a positive slope, a slope that is becoming more and more positive. So now we know we have to figure out the next bit, how long it takes her to get to the rabbit hole. So the rabbit hole is at a position of 30 meters. Oh, we didn't do the acceleration. Let's fill that in. So her acceleration is plus 4 meters per second, so that's up here. Now she travels at a constant velocity for a little while. How long does that take? Well, she needs to get to the rabbit hole, which is 30 meters in total from where she started. She's already traveled 18 meters, so 30 minus 18 is 12 meters left. Well, she got 12 meters left. We're going at 12 meters per second, so she will run for 1 more second at her current speed. So that's 1 more second. Here we go. I'm going to move this tick mark over. This is what you get for having my chalk drawings rather than a nice computer-generated plot, right? So this area of her running at a constant speed is 12 meters. Right? It's a box with a height of 12 and a width of 1. So 18 meters plus 12 meters is 30 meters. This takes her to the rabbit hole, which she would get to at 4 seconds. So we can fill this in here. I'm going to erase this because my my drawing doesn't quite line up. So I need to wind up here. This is just me fixing my art. So I want to be at this point, right? 18 meters, comma, 3 seconds. So here, and then we go a straight line like that. My picture isn't great. This is a concave up parabola, but this is a straight line. Oh, and I was supposed to draw that one in blue, wasn't I? There we go. The acceleration is 0 during that period. So now she runs past the rabbit hole. So her velocity is going to go back down to 0, right? So in the part that I've drawn in red, she slows to a stop. How long does this take? Well, she's going at 12 meters per second. She's decelerating at 4 meters per second every second. So this ought to take 3 more seconds. Well, let's draw that. So this gives me, this time is at 7 seconds total. And so this little triangle tells me how far she runs past the rabbit hole. Triangle, base of 3, height of 12, 1/2 base times height is another 18 meters. So this means she runs 18 meters past the rabbit hole. Okay, we can draw that on our graph too. So here our velocity decreases down to 0. So in the next 3 seconds, she will wind up here. So this is a total of 18 meters past. So I want to draw a concave down parabola in this bit. Now, finally, she runs back to where the rabbit hole is. Well, she's gone 18 meters past it. I might imagine this part and that part to be symmetric because the acceleration is the same. Oh, I haven't finished my acceleration graph, and I keep dropping my chalk. So I need to accelerate at -4 meters per second squared for another 3 seconds. There we are. So if she's got to go 18 meters backwards, we kind of already know these triangles, right? This, if here's a triangle that's another 3 seconds. This is 10 seconds total after she has started running. This triangle has an area of -18 meters. So what does she do? She runs back here, back to the rabbit hole. Her acceleration is still 4 meters per second backwards. So I've kind of figured everything out. Let's make sure. So the questions I've asked, part A, how much time does the rabbit have to duck back into its hole? That's time here. Well, 3 seconds of accelerating, 1 second of running at a constant rate. That's 4 seconds. Position there, how fast she ran past the rabbit hole. That's 18 meters past, or 48 meters total, which I figured out entirely from my graphs. The critical thing to know, the thing that let me do all of this without having to write a single equation, is the connection between the area under the velocity versus time graph and the distance moved. So in the green bit, this is a triangle with an area of 18 meters. I run 18 meters forwards in 3 seconds. Oh, I don't need to draw that as a solid line. So this point is 18, 3. This blue bit is at 30, 4. I've run, whoops, I've switched my X and Y, haven't I? I should put this chalk down and do it properly. So this is 3, 18. area under that triangle is 18. Now, this is 4, 30. I've gone 12 more meters in 1 more second. This is 7, 48, because I've gone 18 more meters forward. Now I go 18 meters backwards. This is 10, 30. No equations involved. If you want to see an alternate solution to this kind of problem with equations, look at my solution video to question 1. Here I did the same thing, except instead of just doing this, I then afterwards did it by writing the kinematics equations that you're familiar with. But you know those kinematics equations just come from looking at areas under curves anyway. So it's really the same thing. My computer went to sleep, so I have to log back in and then end the recording.